So we've talked about acids. We've talked about how to calculate the pH of acids and how to recognize an acid when we see one. We've talked about bases, and we've learned how to determine the pH of a base solution and to recognize bases when we see them. Now we're going to see that there are ionic compounds called salts, and some of these behave as acids and bases. Not all of them do. Some of them are neutral, but we're going to have to be able to look at ionic compounds or salts and determine their acid-base properties. Now let's look at this table, and let's look at it kind of closely here. I don't have, of course, every acid and base known to man on here, but I have a few. I have listed 3 of our strong acids that are on our strong acid list. You'll notice also that I've included H3O+ because every strong acid basically gives you that in solution. So that is as strong as an acid. Anything less than this is going to be a weak acid, okay? As we go over to the right-hand side and consider its conjugate, what is it a conjugate? It's a conjugate base. So when you have a strong acid, its conjugate base is neutral. Would you consider water neutral? Yeah, I would. Okay? And down here, we've got our strong bases. Now, we didn't talk about S2- and O2-. We talked about metal hydroxides and say that any metal hydroxide is a strong base. If you've got a strong base, its conjugate acid is neutral. So what is a conjugate acid? What it becomes after it accepts a proton. Okay? Then you have this whole realm of weak guys, right? You've got your weak acids. If we look over here at their conjugate bases, a weak acid will have a weak conjugate base. And we've got some information we can put up here on the screen. All right? If an acid is strong, its conjugate base has no measurable strength. Okay? You must keep that in mind. That is an extremely important thing. Usually, okay, anions, negatively charged ions, are proton acceptors. What are proton acceptors? Let's write that down. Proton acceptors are your bases. And so you'd say, okay, all of these are bases, but the ones that are conjugates of strong acids are not going to accept the proton, because if they did, they'd become a strong acid, and strong acids 100% go right back over to here. So it cannot accept it. So if an acid is strong, you must remember that its conjugate base is neutral. It cannot accept a proton. Okay? And then the weaker the acid, the stronger its conjugate base, okay? So we see acid strength increasing as you go up here. In other words, as you go down, it gets weaker and weaker. Therefore, your base gets stronger and stronger. So there's an inverse relationship there. All right, so let's think about this. How would we work our way through this? If you saw Br- and you were asked the question, is this acidic, basic, or neutral? As an ion, I will realize that its only choice is to be either neutral or a proton acceptor, a base. It cannot be acidic. We will rule that one out right away. Why can't it not be acidic? Do you see a proton that it could donate? That's what acidic means. Oops, sorry. Acidic means proton donor. So then you are left with B and C. Which one is it? Well, this one is neutral. Whoops, sorry. This one is neutral. Why is it neutral? Because this is a conjugate base of HBr. So you need to go back and you need to review your strong acids. You must know your strong acid list. Okay? So we've got 6 of them that I have given to you. You've got to keep those in mind. You put the proton on and say, what would it be when I put the proton on? If it were to accept, it would become this. This is on the strong acid list, so it cannot accept it. Therefore, it is neutral. The next anion to consider, what is F-? Well, I am hopeful that you picked that it's basic. Why is it basic? Well, again, we can eliminate the acidic because there's no proton to donate. So we choose between these two things. We go ahead and have it accept the proton and think about what that is and say, is it on the strong acid list? No. Therefore, it could accept that proton, and that makes it basic. Now, you've got to know a relationship between the Ka and the Kb of conjugate acid-base pairs. So let's do a little bit of work here back on our board. Let's consider Ha, okay, and what it does when it's in water. And let's consider its conjugate base, A minus, and what it does when it's in water. And I want to write the reaction. This is something you've got to do over and over and over again in this chapter. We don't give you the reactions. We expect you to take them and run with them. So here is the acid. We will add it to water. That will always be my step, okay? Then we let the acid do the acid thing, which is to donate a proton. When it donates, what is it left with? Okay, since it's a weak acid, and I didn't tell you that it's a weak acid, but I am telling you now, if there's a Ka value associated with it, then it has to be a weak acid. And then we're going to have it donate, and that leaves you with A minus. And if it accepted, you have H3O plus. Okay? So this is the acid doing the acid thing in water. Now let's have the base do the base thing in water. You take the base, the proton acceptor. Who is he going to accept from? He's going to accept from water. Water is going to donate, and that's going to give me Ha plus, what does that become after he donates? OH minus. Now what I don't want you to do is memorize these two reactions. So as you write them over and over again, you're going to see commonalities. What did I do in writing these reactions? I said this is an acid. Let it do its acid thing. Swap the proton, what do you form? Don't memorize the products. It should be a logical solution to this being a donor to that. Okay? If it is not logical, get help until it becomes logical. Don't memorize those products. Then this guy, if he's going to act as a base, he's a proton acceptor. He accepts a proton from the water. What does he become after the swap? Now, are these the reverse reactions of each other? No, they're very different. They both have water as a reactant. They have different products. Okay? Now, let us take these two reactions. This one has an equilibrium associated with it, and we call it Ka. Okay? We have the Ka expression. This is Kb. Okay? Because it's the base reaction. Let's take these two reactions and add them together and see what we have. Is there anything that can cancel? Well, this Ha cancels with this Ha. This A minus cancels with this A minus. And we have 2 H2O giving you H3O plus, oops, H3O plus OH minus. Now we've seen that reaction before. What's the equilibrium constant for that? What do we call it? Well, that's called Kw. Okay? Now, if two reactions add to give you the overall reaction, what do you do with the Ks? You've got to go back to a previous chapter when we learned how to manipulate these reactions. What do you do to your Ks to get that? Well, if you can add these, then you will multiply those. So Kw is equal to Ka times Kb. Now, for pure water at 25 degrees Celsius, well, for water at 25 degrees Celsius, whether it's pure or not, that's the value for Kw. And you'll use that over and over again. If it's not at 25, we have to give you the value for Kw. All right, so that is how, and this is really a key relationship that you must commit to memory. You'll use it so much that surely it will be easy to commit to memory. Okay, so I've written that there, and you need to know what its job is. Very often, you know the Ka of an acid, but you need to know the Kb of its conjugate base. You look this up in tables, or it's given to you in the problem. You've got to be able to use this to determine the Kb. We'll practice doing that as we go. Okay, so here's an example, and you're going to work it. See, HClO, it's an acid. It's an acid. It's neutral. It has H written at the beginning. I know it's an acid. I also know it's an acid because I gave you a Ka for it. Now I want you to determine the Kb for ClO minus, its conjugate base. Well, did you get C as your choice? Well, that is the correct answer. How do you get C? Well, you plug in what you're given. You know Kw is 1.0 times 10 to the minus 14. You know Ka is 2.9 times 10 to the minus 8. You solve for Kb. Now, if you take this and divide by that value and don't get that answer of 3.4 times 10 to the minus 7, then you're using your calculator incorrectly, and you need to pop in and see me, and I'll be happy to make sure you're using your exponent key correctly. That is the biggest place that I see students mess up, is they don't plug it in using their exponent key and they end up with some funky value for their Kb. But that is the answer and how you obtain it. So now what do we do with it? Well, if we want to determine the pH of a solution, we would figure out, first of all, what do we have, and then we would work our problem in a very similar way that we did weak acid, weak base problems earlier. Okay, so we're ready to work this problem, and we have got to first establish that NaClO is an ionic compound that's a salt, okay? It's just think of it as an ionic compound with a cation and an anion, and when you take that and dissolve it in water, ionic compounds are always strong electrolytes. So if it dissolves, it's going to break up 100% into its ions. So there are its ions. This is the first reaction that happens when you dissolve sodium hypochlorite into water. 100% breaks apart. Now, we have our salt, okay? We have our cation, we have our anion, and before we write our next reaction, we have to consider these cations and anions and ask ourselves, is it an acid, is it a base, is it neutral? All right, so I look at my sodium and I say, hey, this thing has got no proton, it has no H plus to donate, so it's definitely not an acid. Cations would never accept an H plus because like charges repel, so it's not a base. These 1A and 2A metals are always neutral, okay? So this guy is neutral. ClO minus, it's negatively charged, so we can conceive of it accepting an H plus, being a proton acceptor. It would only do so if in doing it didn't become a strong acid, and HClO is not on my strong acid list, so I know it can accept a proton. It's a proton acceptor, it is a base. Now this reaction happens 100%, so when it says that it is a 0.12 molar sodium chloride, a hypochlorite solution, this is how much I put in. There isn't any of that. Once it dissolves, it all turns into these things. Every one of those makes one of these and one of these. So the concentration of this is no more, and we have 0.12 of this and 0.12 of that. All right? This is neutral, I don't care about. This is a base, so now I'm ready to write the base reaction. Now, the other giveaway that this is a base. Look at the problem. I gave you the Ka of HClO. HClO is not in there, but ClO is. That must be its conjugate base, okay, of that acid. So let's write the base reaction. The next thing you have to do is write this reaction behaving as a base in water, okay? It is dissolved in water, so I'll be good and put an AQ. Water is a liquid. It is weak, therefore there's equilibrium arrows. It is a base, so it is a proton acceptor. Who does it accept from? The water. That makes me form HClO. That is the acid, and this becomes OH minus. Bases should have OH minus in solution because that's a definition of a base too, isn't it? Something when added to water increases your OH minus concentration. It's an equilibrium. So we can do an ICE table. We know that Ka is equal to HClO times OH minus divided by ClO minus. All I've done is done products over reactants raised to the power of their coefficients. I'll come back to that in just a minute. Let's fill in our table. The I initial of ClO is what I have right here. I know that before this reaction takes place, I've got this concentration of ClO. All right? Don't care about the water. Before anything happens, this is 0, and this is almost 0. Remember, it's 1 times 10 to the minus 7 in pure water, so it's a really tiny number. We can use 0 there. I consume some of this, 1 to 1 to 1, so I produce and I produce. This leaves me with 0.12 minus x. 0 plus x is x. 0 plus x is x. Now I'm ready to plug everything into this expression here. What was the Ka value? Well, we figured that up on the previous screen, right? The Ka value was 3.4 times 10 to the minus 7. So I'm going to put 3.4 times 10 to the minus 7 here. HClO is x. OH minus is x. So it's equal to x squared over 0.12 minus x. Now look at that value of K. Very small, with a significant amount of initial concentration. So I will make my assumption, okay? What do I assume? I assume that x is much, much smaller than the 0.12. And you can't see that, so I will try again. We'll write it right here. Assume that x is much, much smaller than 0.12. Okay? What does that allow me to do? That allows me to ignore that term. Okay? So we'll get rid of that. So to solve, I will take 3.4 times 10 to the minus 7 times the 0.12, and that is going to equal to x squared, right? I just multiplied this to the other side, and then when I take the square root of both sides, I will have x. And the value of x is 2.0 times 10 to the minus 4. Now don't ever get to this point without checking your assumption. Is this much smaller than 0.12? Yes, if I were to subtract, like I ignored it here, if I were to take 0.12 minus 0.0002, I would still have 0.12 as my answer to 2 places past the decimal point. So it was a good assumption. Boom. Now, because we're evil, sometimes on the test that'll be one of the answers, because students get to the x and hallelujah, I've got an x, let's move on. That's not the answer. Always check. What did they ask? Go back to the problem. They asked, what is the pH? So I have an x. How is that going to get me to the pH? I come back here and look at what x is equal to. It is the concentration of OH minus. So if I took the negative log of 2.0 times 10 to the minus 4, what would I have? I would have the POH, right? And the value for the POH is 3.69. Okay? That might also be a choice on the exam, because students take their x and take the negative log and don't even think about what it is, and they assume that that must be the pH. But that's the POH. So our last step would to take that number and do what in order to get the pH? Well, we'll take that number and subtract from 14. We know that POH, let me just write it over here, okay? POH plus pH is equal to 14. So 14 minus POH, which was 3.69, is equal to pH. And that's what's being asked for in this problem, and the answer is 10.31. Now let's think about it. Is that a reasonable value for pH? 10.31, if it's above 7, it's basic. Did we establish that this solution should be basic? Yes. Is this a base reaction? Yes. Did it increase the OH minus concentration? Yes. It's a basic solution, so we should have a pH above 7, and that is the correct answer.